Navigating a massive, undocumented codebase is a search for logic buried under years of overlapping instructions. You are constantly hitting dead ends, while trying to untangle how a single component functions. Python code functions as a bridge between the interpreter and the developer. It is a communication protocol that allows a team to understand the system's logic years after the original instructions were written. Prioritizing quick execution over readable, logical structure accumulates technical debt. We are borrowing time from future maintenance to push a feature today. This debt builds up silently. New features take longer to implement, and eventually pushing a minor update starts breaking components in unrelated parts of the system. Technical debt represents a structural failure in how information is passed between developers. It increases the cost of keeping software alive. Mitigating these faults requires a rigid architectural approach. We move away from ad hoc defensive programming and toward a design-by-contract model, where every component follows an explicit set of rules. Our goal is to build a robust Python application, where adding a new event type requires zero changes to the core execution engine. This reconstruction relies on the solid principles. We will focus on the first three: single responsibility, open-closed, and Liskov substitution. Systems built on ad hoc patches eventually collapse under their own weight. Long-term stability is only possible through a modular architecture defined by strict boundaries. Consider this system monitor class. It loads data from a source, identifies specific events within it, and streams results to an agent. Consolidating these three distinct tasks into a single entity creates high architectural coupling. Every task is physically dependent on the code of the others. This creates an immediate risk. If the format of the external log files changes, we must modify the same class that handles core logic. A mistake in the loading code can now corrupt the streaming engine. We apply the single responsibility principle to fissure the monolith. Each new object now handles only one vector of change. If we overhaul how we ingest data, we only modify the activity reader node. Because the responsibilities are separated, the alert system and system monitor nodes continue running without any changes to their source code. Isolating responsibilities contains the impact of any future modification, protecting the system's structural integrity. Inside the isolated system monitor class, we find the identify event method. This method evaluates specific dictionary keys, checking if a session went from 0 to 1 for a login or 1 to 0 for a logout. But this design can't scale. To add a new event type, developers must manually alter this central logic chain. This violates the open-closed principle. The core method remains open to continuous modification, increasing the chance of introducing bugs into the existing login and logout logic. Hard-coded logic trees punish growth. An application is fragile if its core engine must be surgically altered for every minor update. We solve this by moving from procedural logic to an abstract base class pattern. Instead of a central master function, we define an abstract event and move the specific conditional logic into discrete subclasses. We use the Pythonic __subclasses___ method to dynamically iterate through all supported events. This loop evaluates incoming data against the subclasses. The monitor executes the check without needing to know which events are supported. We can now add a transaction event straight into the codebase. The monitor automatically detects it and includes it in the loop. By relying on polymorphic relationships, we achieve a system that allows for horizontal extension without requiring changes to the existing logic. However, these dynamic architectures introduce a new risk. Subclasses can be written in a way that breaks the expectations of the base system. The Liskov substitution principle states that any subclass must be perfectly substitutable for its parent class without causing the program to fail. This requires a structural contract. For example, a subclass cannot suddenly demand stricter input requirements than the base class it inherits from. Look at this signature mismatch. The base event class accepts a dictionary, but this login event subclass overrides the method and requires a list instead. Python's interpreter won't catch this contract breach during development. It will only surface as a crash at runtime when the system tries to pass a dictionary to that specific subclass. To prevent this, we use static analysis tools like MyPy to verify our class hierarchy. MyPy checks the hierarchy against our type definitions before the code runs. It identifies the mismatch and flags it as an error. True extensibility depends on the structural consistency of Listkov substitution. It ensures that every new component behaves exactly as the system expects. We have transformed the system from a tangled monolith into a modular ecosystem of isolated components. Isolating responsibilities through SRP ensures that changes to our data sources do not cause bugs in our business logic. Dynamic subclassing through the open-closed principle allows us to build new features in parallel without modifying a central logic file. And static verification of our contracts ensures that the system remains stable as it grows. Standardizing these patterns moves code quality beyond subjective preference. Maintainability is the result of low coupling and high cohesion, structural traits enforced through clear architectural contracts and